Hello, my friends. I wanted to take some time to address the mass spring problem set, in particular, number two. I think that number one is pretty straightforward, but number two is not really straightforward. And you might miss some things along the way. So, this is to help guide you in working this through. And I don't mind giving you some of it too, especially if you've taken the time to listen to this and work with me. So let's take a look at number two. Got this non-homogeneous differential equation. We know that A and omega positive constants. And we also have this initial condition, two initial conditions, that both x and its first derivative at zero are zero. So the first thing we have to do here is find the function that solves this initial value problem. So we're going to have an xh and we're going to have an xp. Now, xh is going to be based off the left-hand side, and that's going to be a plus or minus 3i root there. And on the right, and this is something I should have said, is that we're going to assume for parts, all except the last one, that omega is not equal to 3. Because if omega is equal to 3, we have a repeated root on the right, and we want to have that in the very last part of this problem, but we don't want to have that before then, as we're letting omega move back and forth. And it'll become apparent why we don't want it to be 3 as we work through this. So on the right, I have this cosine of omega t, and that corresponds to a plus or minus omega I. Now, that means that my xh is going to be c1 cos 3t plus c2 sine of 3t. And then my particular solution, we already have an a as a parameter in the problem, so we're going to start with b cosine of omega t plus c sine of omega t. And then we're going to solve for b and c. Before we do anything else, we want to find out what the b and c are in terms of that just for this problem. So that means we have to crank out the second derivative, and you should work through this and convince yourself that this is all true. But the second derivative of our particular solution guess is going to be negative omega squared b cos omega t minus 9 omega squared c sine of omega t. And please show the work for that. Just show how to get there, especially since I just gave it here. And then we're going to take that plus 9 times the original x guess, which is going to be 9b cos omega t plus 9c sine omega t. And we're going to combine those together so that we get xp double dot plus 9xp is, and then when we group these all together, we're going to get 9 minus omega squared b, there's a b there, cos omega t plus 9, what the hell is this? Wait, there should be new 9 right there. I got a little excited or something, I wrote that early. So 9 minus omega squared c sine of omega t. And we're going to compare that to what we're given, which is 4a cos omega t and 0 sines of omega t. So that tells us immediately that c must be 0 and b must equal 4a over 9 minus omega squared. All right, so now we actually know what xp XP looks like. And I'm going to go back up here and put that in. I'm trying to keep on the same page as much as possible. But XP now looks like this: 4a over 9 minus omega squared cosine of omega t. Let's get rid of all the rest of this stuff here. So that means our complete solution is going to be the sum of the homogeneous and particular parts, and that's C1 cos 3t plus C2 sine 3t. And yes, now I'm just making sure that, okay. Yep, this is looking good. Sorry, I'm looking at the assignment, making sure things are lining up here. And by the way, I just didn't feel like having the video on right now. I thought this, just switch it up just a little bit. So I didn't finish adding this on here. So then plus 4a over 9 minus omega squared cosine of omega t. Using the initial conditions now to find C1 and C2, and you need to show the work for this again, but what we can show is that C1 is negative 4a over 9 minus omega squared, and C2 is 0. So we get x is equal to negative 4a over 9 minus omega squared times cosine of 3t, and then also times, well, here, let me just write this out. I'm factoring out that 4a, negative 4a times over 9 minus omega squared. So we're going to have that out in front, and then cos 3t, and then minus cos omega t. And I don't like that negative out in front, so I'm going to absorb that into the difference in the middle and just flip that subtraction. Like so. And then I'm going to use the identity that's given in the handout to combine these two cosines of different periods. So what that's going to give me then is x is equal to 4a over 9 minus omega squared. And from the formula, we've got a negative 2 sine of 1/2 the sum of omega t and 3t, and you can pull out the t, so we get omega plus 3t there, and then another sine of 1/2, and it's going to be the difference. It's going to be omega minus 3t. And then I would like to get this a little nicer, so that's going to be negative 8a over 9 minus omega squared sine of omega plus 3 over 2t sine of omega minus 3 over 2t. All right, so that is basically the answer to part B, or it's most of the way there. The one thing we haven't talked about is what the envelope is. So, and that's kind of an important concept here. So let's take a look at our answer. Clear that all up. And of course, you can pause this if you need to like look at anything I've got here longer than I'm keeping it. So we've got these two signs, and this one has period 2 pi over omega plus 3 over 2, which if you think about it is 4 pi over omega plus 3. And then in a similar way, this one over here is going to be 4 pi over omega minus 3 as its period. Since omega is positive, the omega plus 3 is going to be the larger quantity, which makes this smaller than this one. And so that means this one is the long period out of the two. And that's what we're going to use for our envelope to describe our envelope. And what we got here then is x is equal to, and I'm going to distinguish the envelope part. And then I'm going to do something a little crafty, maybe. So right off the bat, let's see, is that the, yep, 2t. So we got that. This is my envelope. This governs the amplitude of this following sign, the short period sign, which is omega plus 3 over 2t, like this. So this number out in front acts like an ever-changing amplitude for the other sign. Now it's got that negative in there. Oh, screw it. I'll just leave it there. But what I want you to then do is make a nice graph of this. So do the envelope first. Again, the period on this thing is going to be 4 pi over omega minus 3. So it's going to be a sine curve between 0 and 4 pi over omega minus 3 of amplitude 8a over 9 minus omega squared. I'm going to take the absolute value there. Just because if omega is bigger than 3, then that quantity changes sign versus when omega is less than 3. And we want to have this be as legit as possible. Again, now you can really see here, and I probably should have noted this earlier, omega can't be 3 to perform that division by 9 minus omega squared. So we needed that assumption, and you might have worked this through without making that assumption, which was what I guess I was hoping until I met with someone today and we talked about it, and I don't think it's obvious, hence this video. So now inside here, I've got a period, one period sign. I'm going to do this in green. And you know, you can do this nice. Did I even ask you to do this? Well, I didn't ask you to graph shit. But you can definitely put this into Desmos and it looks pretty sweet. Maybe we'll take a look at that. So for an envelope, it governs the magnitude. So it also governs the magnitude when things are negative. And what I'm basically saying is I'm going to sketch this other sign and have it encased by that green envelope down there. So this sign has a period of omega, wait, what was it? This one had a period of 4 pi over omega plus 3. Now, we don't know what the hell omega is. So it's really hard to do this in a precise way. And what I'm going to do is just wing it and just say, you know, there's a sign that lives inside this green figure 80 thing that I've got going on here. And so every time it wants to hit a max, it's going to be bouncing off of that curve. You son of a gun. Sorry, I hate that straight line thing. I can probably turn that off. I guess I can't slow down. Keep going, don't slow down. We see something like that. And eventually this will be periodic. That actually is not too bad. It almost looks periodic right there. Sometimes it takes a while for the period to manifest. It has to do with the least common multiple of this quantity and this quantity, but they're maybe not even integers, probably not even integers. So anyway, don't get too stressed out about that. I would like to show you what that looks like. So we've got a Desmos graph right here. So let's see here. So check out what I've got up above. This is the simplified version of what we've just seen. I'm using W instead of omega. And down here, we can see the graph on this thing. And I've got omega set at 2.7 as a minimum here, just so we were seeing what happened as we approach 3. Look at where that first period ends. It's at 20 seconds roughly. As I increase this period just a little bit, so we're at 2.7. If I go to, I just want to be 2.8. If I go to 2.8 now, that period ends at, you know, so like 32. if I go to, is it going to let me type? Okay, whatever, I'll type it in. So I go to 2.9 and it jumps even more, all the way up to 60 something. And then when we go to 2.95, which is what I'm going to do here, look at that. Do you see that? That is incredible. So what we've got was, so we're right up on 3, and that period is out to like t equals 125, 126 seconds or something like that. And this just keeps going. The closer and closer I get to 3, so let's do one more. Let's do something. Boy, I'm scared to put a 9 in there, but oh, look at that. I did it. It worked. So, oh my God, isn't that beautiful? Look at that. We're at omega's 2.99. Let's see where that first period ends. Look at that. Way out at, near 628, around that area. So, and we've seen this, the closer and closer you get, if we want a little bit more, and I'm just going to do it because, I got Desmos all revved up here. Holy shit. So there's omega is 2.999. And look at the picture right now. Notice how the edge of that envelope looks like a straight line. And it is approaching a straight line. And in fact, it doesn't start to even curve. And it's starting to see a little curvature there as I move out, and it's actually quite beautiful. So let's zoom out just a little bit. And we see that with the envelope has grown huge. That is one big ass fish. And what do we got? Where are we at out here? We are in the 6,280s. So if I added another 0, you can imagine this would leap even further. I'm not going to do it. I'll let you do it. I mean, you can try this experiment yourself, and you should, because Desmos is a thing you as a math person should be messing with on a regular basis for recreation. My friend, you should be recreating with math. It's good for you and soothing in many ways. Makes you powerful and soothed. And I'm looking at the assignment right now to see what else we got here. Boy, that we've really knocked out a lot. So you should easily be able to answer D and E from that, and graph those solutions using Desmos. Cut and paste those or something into your assignment. You don't have to do them. I guess I say include rough drawings, so I won't take that back, but use Desmos to explain essentially what I just explained to you in your own words. Don't use my words. I'm not going to remember what my words were, but I'll know. I'll know. So then the last part, and the very last part of this, we've got to redo the problem. So we've got x dot plus 9x equals. Now we're going to replace omega with 3. So we've got 4a cosine of 3t. I'm not going to do all of this one for you because I want you to work this through, and it's just tedious, and it will require patience and just care. So the left side again is a plus or minus 3i root. On the right, we now have a plus or minus 3i root. We have a repeated root. So x is going to be, xh is going to be our classic cos of 3t and sine of 3t. But now xp has got, and let's not use a again, let's start with b. So we've got b t cosine of 3t, right? Because it's a repeated root. So now a t manifests in each of those in front of each of those functions for a repetition. Remember that straight line on the envelope? There it is. That's the straight line. It's going to be some weird slope that you're going to have to work through, but you can figure this out again. So now, oh shit, okay, let's kind of go through this because I want you to at least see how to do this. Okay, so we're going to solve for B and C. So let's see if anything really nice happens. We had these initial conditions. I'm such a pushover. I'll just do anything for you guys, as long as it's fun. All right, so then see here. So in x of 0, so we're going to do, oh shit, no, we got to take the derivative. So let's see here. Xp dot is P, product rule. I'm going to go fast so you can figure this out on your own. Think it through. Hopefully you can do the product rule relatively quickly. And what I'm writing here is something you should do on your own. Whoa, dude. Okay, there's two cosines. There should only be one. I was blabbing too much. Got myself confused. So that, yeah, so that's our XP, because we got to have a sine and a cosine of 3t. So then this one's going to be sine of t plus t, 3t, cosine t. Cool. And shit, let's just do the freaking second derivative here. Notice how I'm just keeping everything all nicely grouped like that, so that we don't go insane. Screaming into the night. And let's see here. So then we got minus 3 sine 3t, and then do. What did I just did the t? So now I'm doing the sine, and that's going to make a 9 cosine of 3t there, and then plus c times 3 cos 3t. See how pretty it is? Look at the symmetry in the way these two solutions turn out. And then that's, again, wait, I got it. So that is a minus there. Okay. Minus 9t cosine of 3t. Yeah, good. So we've got to now take 9 of the originals. So I'm going to add to that 9 of the originals, which is 9 bt cos 3t plus 9 ct sine 3t. That's a really tiny little c. It's the same c as above. It's just off in the distance or something. And I'm going to add those up and group like terms. And I'm going to group by function. There's only 4 different functions floating around here. There is a cos of 3t. There is a sine of 3t. There is a t cosine of 3t and a t sine of 3t. And if you've been around, for the last couple of weeks, you've probably heard me say that the t cosine of 3t and t sine of 3t should die here. So I'm really hoping their coefficients cancel out. And if not, I probably screwed something up. So let's group and take a look. It's not a plus. It's a t. Boy, I hope that, but look how tiny that last one is. I better be a 0. So cosine of 3t's, we've got a, where are we at? Okay, cosine of 3t's. We've got 6 of them right here. So there's just going to be 6c right there. Sines of 3t, I've got -6 of them right there. -6b of them. Here comes the moment of truth. I've got, wait a minute, there should be a t there. Okay. That should have a t in front of it. That 9t, that should be -9t cosine of 3t right there. And when I say right there, I'm talking about, I think in blue, there's a t that I didn't write in there when I differentiated. So so I've got -9b of those plus positive 9b of those. Oh, hells yes, that's a 0. And then this one also turns out to be 0. I believe it now that one did. So check out that we've got it now. We've actually got what C and B should turn out to be. I got to clean up some of this because I need more room on here, and I'm afraid I will forget, and it'll just take too much flipping back and forth. So comparing what we have at the bottom of the screen to the thing on the right, the 4a cosine of 3t, we immediately, can I go back? Yes. Huzzah. We immediately see that 6c needs to be 4a, and negative 6b better be 0 because there's no signs of 3t on the right. So now we get c equals 4a over 6, 2/3 of an a. Look at that. That is not too bad. So now our xp is going to equal 2/3 t sine 3t. Yep, sorry, I'm just checking everything. Looking good. What? Wait. Hold on. I got myself fucked up there. Oh, I made a promise I wasn't going to cuss too bad in this, and I just broke it. I hope that's okay with you. Okay, sorry, I got myself a little tossed around here. Oh, right. So, yep, that is all good. So, yep, okay. Yep, I'm happy with that now. So xp is 2/3 t sine of 3t. And that means our x is going to be c1 cos 3t plus c2 sine 3t plus 2/3 t sine of 3t. Now we got to find c1 and c2. Those are coming from our initial conditions. So let's, when you put in t equals 0, you get c1 equals 0. And when you take x dot, let's just do that. So first off, we know this is going to be 0. That'll have to be 0. And then x dot is going to equal negative 3 c1 sine of 3t plus 3 c2 cosine of 3t. And then this dude is going to turn into a gosh darn product rule. So that's going to be 1 sine of 3t plus 3t cosine of 3t. Well, I'm having a good time here. So now we put in 0, and all the signs are going to die. And what'll be left is the cosine. And so we've got 0 equals 3c2. But notice that when I put in t equals 0, that also goes down. So we just got 0 equals what? Wow. Is this possible? Is xh... I'm checking this out. Right now, it's seeming like c2 is going to be 0 as well. Is that believable? Yeah, that's crazy. So I think here that the homogeneous parts, and I've got to, you know what? I'm going to double check this. We've taken the time to get this far. I'm just a little concerned about it. And why don't I have an A in there? There we go. So there should have been an A in there. That was 2/3 A. All right, so x at 0 equals 0. That definitely gives c1 equals 0. That's a no-brainer, or a lesser, smaller brainer. And then x dot, well, we already know c1 is going to be 0, so we can actually just forget about that. We don't need that anymore. And so this is going to be 3c2 cos 3t plus 2/3 a times, now I do this damn derivative again. Derivative t is 1 times sine of 3t. Boy, I think I got that right the first time. That's incredible. Actually, it's very shocking. So when you put in t equals 0, the signs die. Sign dies, this dies because it's multiplication by 0. C2 is freaking 0. So wow, this is extraordinary, is that X is actually just the XP. How cool is that shit? So there's 2/3 AT sine of 3T. Find the envelope. That's all you got to do now. Where's the envelope? Hint, it's this. Okay. So if you sketch this thing out, what you would have is an envelope which is just 2/3 AT. So that's a line, right? X equals 2/3 AT. And we're going to do the plus and minus version of it. It's just a slope, a line of slope 2/3 A, and then negative 2/3 A for the bottom of the envelope. Inside here, I have got a sine curve of period 2 pi over 3. Growing louder and louder and louder. And this is 2 pi over 3 right there. And this is 4 pi over 3 right there. And this is, let's just write the envelope equation right on the side. And this is equals negative 2/3 AT. And A is positive, so that's completely labeled consistently. And we've just done the whole part on that, friends. So hopefully you can use this information to help you get through this. If you're stuck, this can help you through it, but this should allow everyone to have a fun time with this. But now, you know what? I'm going to tell you more. I want to tell you this because I got you. So what is going on here? Let's look at this equation again. I already lost what is here. 4a cosine omega t. So over here, this thing has solutions that are like this. And they have periods of 2 pi over 3. And the frequency is 3 over 2 pi. So we can think of that as the frequency, the number of cycles per second, hertz. This is frequency. Over here, we've got a thing with frequency 2 pi over omega, aka frequency equals the reciprocal of that. So omega over 2 pi hertz. We can think of the left-hand side of this, just the homogeneous part, as representing the structure of some object. And let's think of it as a very fragile crystal glass over here. So we've got this very nice crystal glass sitting over here, and its natural frequency, everything has a natural frequency or frequencies, and if you hit them, you can get that thing to react. So over here, let's assume this thing has the frequency 3 over 2 pi, and it's modeled, its resonance properties are modeled by that equation. So now what are we doing on the right? Well, we are forcing that thing with a different frequency. So think of this as a person over here who's singing a note. And they're singing this note of different frequencies. And they start off with a low omega, maybe. So they're starting off with omega less than 3. And they're very good singers, unlike what I'm about to do to you. They start singing and they increase the pitch of the note. They up its frequency. And as they do, it starts to affect this glass. And at first, when they're really close to it, but not right there, the glass will be like kind of undulating a little bit. That corresponds to that envelope that you see in the first part of this solution here. That looks super shitty. But what you see are the envelope oscillations. That's what you really sense. You don't sense the higher frequency thing. You catch this kind of meta frequency that's being produced. So as you're saying here, and get close to that frequency, what you see is resonance approaching. So eventually, the minute you get there, the envelope on the response in that system is unbounded, increasing oscillations. And at that point, the structure can't hold it, and you'll see this glass just crack and break because it has no option to deal with the resonance other than to end its existence, as you might want to do after hearing me sing that scale. So that's it, friends. Hope you're having a good one. I'm going to end this right now, and I will see you in class. Be well.